compact surface. So it will give you, for instance, the cases of n equals 2 but degree 1 and 2. Those are actually Riemann surfaces with no holes. So degree. So what we need is the genus of the surface given by the complex points. Okay, so you see how we went from a curve that's a line, but now we go to the complex numbers that we have 2 dimensions, 2 real dimensions, so we all of a sudden we get surfaces. So the genus of the surface is the number of holes the surface has. So when n is 2, the degree of f is 1, 2, you get spheres. Okay, and the genus is 1. When the degree of f is 3, something 4, what you get is elliptic curves. An elliptic curve over the complex numbers is actually a torus. It has 1 hole. Okay? Oops. Okay? And higher genus, which is what you typically observe when the degree of f is bigger or equal to 5, it will be just one of these drawings like that, okay, with a bunch of holes. The very first printing of the book had no picture of these, and somebody wrote to me very angry that, how did you not include pictures of the holes? So there is a new reprinting with the picture of the holes of the book. Okay. So what happens when you have more than 1 hole? So there's a theorem of faultings that says that if your curve if you have at least 2 holes, then you must have only finitely many points. That's only finitely many cubed rational points. Okay, so in a sense, what I was going to say also is that, well, we don't know, we have some methods on how to find points on curves of higher genus, but it's like you have 2 little tweezers and you pick very carefully what curve you can do, and sometimes it works, sometimes it doesn't. So we're starting to know some ways to do this, but the silver lining is that we're not missing much, because any of those curves have at most finitely many cube rational points. So at least we're not missing infinitely many points on those curves. So in a sense, the elliptic curve case is the richest of them all, because all the possibilities can happen. You can have no points, finitely many points, or infinitely many points. And everything else after that, you have to find finitely many points, and that's it. There is no curve out there with genus bigger or equal to 2 with infinitely many points. Again, we would be also just as interested, very interested in being able to find those points. For now, we are doing one thing at a time and trying to solve what happens with the elliptic curve. Okay, so back to elliptic curves. This is a good point for questions. It's a good rational point in the talk. Do you have any questions so far? Yes.
Is there any bound on how many solutions we might want to know we can get all solutions, or because we know that one point won't get us all solutions?
A bound in what case?
Like with where in previous cases, if we had one solution, we could find all of them. Is there like, if we get 5, we can get all of them?
So there are, this is something I was not going to mention, but since you asked, I will mention. In the elliptic curve case, there are some bounds. So Baker proved that for the integral points, at least, for the integral point, there is a bound. So if you give me an elliptic curve, I can give you a bound. Now, the bound is something like, this is section 2.3. It's something like the maximum value of x or y in absolute value is e to the 10 to the 6 times, in the exponent, the maximum of a or b to the 10 to the 6. So Baker proved that if xy is an integral point, then the maximum of x or y is less or equal to e to the 10 to the 6 times the max of a and b to the 10 to the 6th power. So yes, there is such a bound. Completely useless. But there is such a bound. There are some conjectures, in fact, that that there is a bound like that, a little better than that. But the conjecture is that it's pretty bad in general. And you can see also, there's an example here. There's a bunch of examples like this. People are amused by finding equations that have small coefficients, but the first solution you find is very large. And if I remember correctly, this elliptic curve has, the first solution has like
0, 0.
it has
Non-torsion.
and then beyond that, there is a generator of the points that are of infinite order. That point we'll see it has point order 2. So the ones that are of infinite order, the generator has some enormous x coordinate in terms of like the number of digits of the numerator and denominator. So yeah, there are some bounds, but even those are just they seem like it's really hard. You need something else because they get very bad. It's not that Baker's bound is just okay. You just prove something theoretical, and this was a huge breakthrough. But it's not just something theoretical. The points can be really, really tricky like that. Okay, so all right. So what I was saying before was that we have defined elliptic curves in 2 ways. That's no good in math. So unless they're equivalent. So an elliptic curve now is a cubic, a plane cubic that is non-singular and has at least 1 point. But then we defined it in some very short way before. So it turns out that there is always a transformation that brings you, there's an algebraic transformation that brings any cubic, no matter how complicated it seems, that brings it to the short form that I wrote before. Okay. I'm not going to explain that. Instead, I will post a handout on how you do it. Okay. So my friend Ryota Matsura wrote this little handout, and it's very handy. So you can always find an algebraic transformation, some map that brings it to what's called a body stress equation. Okay. For example, This is explained much better in the notes. You might be interested in numbers that are the sum of two cubes. By the way, something that I'm not sure we've done a very good advertising, that on Friday at 7:45 p.m. we will be showing The Man Who Knew Infinity. There's a movie that was in theater, Jeremy Irons and guys from Slumdog Millionaire, which by all accounts was very good. So we're going to show that movie, and then Ken Ono, who will be here for the conference, who is a big name in the theory of modular forms, he was one of the producers of the movie, and he will be doing a Q&A after the movie. So this is, by the way, it's not out in like DVD or something. It's a theatrical showing of the movie just for us. It was not easy to accomplish. Okay, so go see it and enjoy it. All right, so the famous taxi cab numbers, for instance, you can put 1729 in there and try to find out what are the integral points in there. And Romanujan would say, you know that, well, you know the story. But we actually, all the software is better suited to work with short value stress equations. So how do you do that? Well, you can actually show that this elliptic curve transforms to that one via, this is the algebraic map I was talking about. Like this, and then do arithmetic on that one. That is, that all the software packages are happier with. Let's see, a lot of mistakes. Yeah, in any case, what I had there before it kicked me out was so the competing software that Harris was talking about was Magma. There are other things called Magma, so we just put Magma. It shows you no candy, I don't know why. Okay, so let's see if I can do this quickly. So first I'm going to define, Harris was saying like, oh, but Stitch is free. Well, Magma has this online calculator that is free. There's a limit on the computations, but there's a lot of things that goes really quickly, and there's a lot of things that you can do just with this calculator. You don't have to have anything installed on your computer. You don't have to log in. You don't have to wait. It's pretty good. Elliptic curves naturally live in projective space, and that's something I have not emphasized, but all my curves are projective. Right? I always have to look at infinity, that I don't have singularities at infinity either. So I'm going to define projective space over the rationals and of dimension 2. Okay, I like to submit just to make sure that that nothing is wrong. And then I'm going to define a curve over this projective space with that equation, minus 1729 z cubed. Okay, so that indicates it. Good. Okay. So what do I want to do? I don't want to do this one. I want to work with a short value stress model. So I'm going to call it E. I'm going to transform it. So I'm going to call it C. But to do this already, it's telling me, are you sure it's an elliptic curve? Then you better give me a point. So is there a point that I can give it? Sure. I don't know. Let's say I don't know the Ramanujan stories. I don't know how 1729 is a sum of two cubes. But there is a simple one that is 1 minus 1, 0. Okay, that's a point. Okay. That's a point at infinity in my curve. So that's good enough. And then call it, let's see what it does. So what that does is give me a value stress equation. There is a y here. We'll mention that in next time, that the value stress equations come in two flavors, long and short. But basically, this is almost as good. The only thing is that these denominators I don't like too much. So what I'm going to do is do a minimum model, so it finds a better model of that, get rid of denominators and so on. And now it gives me an elliptic curve that that has the smallest possible coefficient that is isomorphic to the one I started with, and now I can do computations on that one. This thing right here, when I did that, it actually something was hidden that it actually also gave me the map, the algebraic map that goes from one to the other. So now I can compute in the new curve, do math in there, and then send things back to the old curve and do computations like that back and forth. All right, I'm going to stop here. There is a homework set here. Liang prepared some exercises and printed a bunch of them. These are also on the website, Liang?
Yeah, just close it.
These are also on the website, but if you want a physical copy, there are copies here for you to take. Okay? So we'll continue tomorrow.